In this video, we're just going to go over a basic introduction into limits and how to evaluate them analytically and graphically. So here's a simple example. Let's say if we want to find the limit as x approaches 2 of the function x squared minus 4 divided by x minus 2. So how can we do so? Well, one way is to use direct substitution. If we plug in 2, notice what will happen. 2 squared is 4. 4 minus 4 is 0. So 0 over 0 is undefined, which we don't know what value that represents. Now sometimes you could find a limit by plugging a value that's close to 2. And that's what you want to do. You want to plug in a number that's close to 2 but not exactly 2. So for example, let's call this f of x. So let's calculate f of 1.9. And let's see what's going to happen. Actually, let's make it 2.1. So let's get a positive answer instead of a negative one. (2.1) squared minus 4, that's about 0.41, and 2.1 minus 2 is 0.1, so this is going to be 4.1. Now what if we pick a value that's even closer to 2? For example, let's try 2.01. So if you type this in the way you see it in your calculator, you may have to put this in parentheses. You should get 4.01. So notice what's happening. As we get closer and closer to 2, the limit approaches 4. So we could therefore say that the limit as x approaches 2 of this function is equal to 4. And this technique works for any limit. As long as you plug in a number that's very close to whatever this number is, but not exactly that number, if the limit exists, it's going to converge to a certain value. Now sometimes you have to use other techniques to get the answer. In this particular example, we could factor. X squared minus 4, you can write it as x plus 2 times x minus 2. Now we need to rewrite the limit expression until we replace x with 2. Now notice that we can cancel x minus 2. So when this term is gone, we can now use direct substitution because the x minus 2 factor was giving us a 0 in the denominator, which we don't want. So now all we need to do is find the limit as x approaches 2 of x plus 2. So now we can replace x with 2, and 2 plus 2 is 4. And so that's the limit. It approaches a value of 4. Now let's look at another example. What is the limit as x approaches 5 of x squared plus 2x minus 4? So notice that we don't have a fraction. We're not going to get a 0 in the denominator. So for a question like this, you can use direct substitution. So all you got to do is plug in 5. So it's going to be 5 squared plus 2 times 5 minus 4. So that's 25 plus 10 minus 4. And 25 plus 10 is 35. So the limit is going to be 31. And so that's it for that example. But now what about this one? What is the limit as x approaches 3 of x cubed minus 27 over x minus 3? Now if we try to plug in 3, it's going to be 0 over 0, so we don't want to do that. In this case, if you have a fraction like this, see if you can factor the expression. So how can we factor x cubed minus 27? So what we have is the difference of cubes. And whenever you see that, you can use this formula. A cubed minus b cubed is a minus b times a squared plus ab plus b squared. So in our example, a to the third is like x to the third, and b to the third is 27. So a is the cube root of x cubed, which is x, and b is the cube root of 27, which is 3. So this is going to be x minus 3, and then a squared, that's x squared, and then plus ab, so that's 3 times x, and then plus b squared, or 3 squared, which is 9. So now we can cancel the factor x minus 3. So what we have left over is the limit as x approaches 3 of x squared plus 3x plus 9. So at this point, we now can use direct substitution. So it's 3 squared plus 3 times 3 plus 9, which is 9 plus 9 plus 9. Adding 9 3 times is basically multiplying 9 by 3. And so this limit is equal to 27. Now here's another problem that you can work on. So what is the limit as x approaches 3 of 1 over x minus 1 over 3 divided by x minus 3? So for these examples, feel free to pause the video if you want to and try these problems. So in this example, we have a complex fraction. So what do you do in a situation like this? If you get a complex fraction, what I recommend is to multiply the top and the bottom by the common denominator of those two fractions. That is, by x and by 3. So I'm going to multiply the top and the bottom by 3x. So if we multiply 3x by 1 over x, the x variables will cancel. And so what we're going to have left over is simply 3. And if we multiply 3x by 1 over 3, the 3's will cancel, leaving behind x, but there's a negative sign in front of it. Now, for the terms on the bottom, I'm going to leave it in its factored form. So notice that 3 minus x and x minus 3 are very similar. If you see a situation like this, factor out a negative 1. If we take out a negative 1, the negative x will change to positive x, and positive 3 will change to negative 3. So notice that we can cancel the x minus 3 factor at this point. And so what we have left over is the limit as x approaches 3 of negative 1 over 3x. So now we can use direct substitution. So let's replace x with 3. So it's going to be 3 times 3, which is 9. So the final answer is negative 1 divided by 9. So now you know how to evaluate limits that are associated with complex fractions. So here's another example. What is the limit as x approaches 9 of square root x minus 3 over x minus 9? So what should we do if we're dealing with square roots? What I recommend is to multiply the top and the bottom by the conjugate of the expression that has a square root. So the conjugate of square root x minus 3 is square root x plus 3. So in the numerator, we need to FOIL. So the square root of x times the square root of x is the square root of x squared, which is simply x. And then we have the square root of x times 3. So that's going to be plus 3 square root x. And then these two will form negative 3 square root x. And finally, we have negative 3 times positive 3, which is negative 9. Now on the bottom, I'm not going to FOIL the two expressions. I'm going to leave it the way it is, because my goal is to get rid of the x minus 9. I want to cancel it. So now negative 3 and positive 3 add up to 0. So what we have left over is the limit as x approaches 9 of x minus 9 divided by x minus 9 times the square root of x plus 3. So now at this point, notice that we can cancel x minus 9. And so what we have left over is the limit as x approaches 9 of 1 over square root x plus 3. So now what we can do is replace x with 9. So I'm just going to continue up here. So it's going to be 1 over square root 9 plus 3, and the square root of 9 is 3, and 3 plus 3 is 6. So the final answer is 1 over 6. Now let's look at this example. What is the limit as x approaches 4 of the expression 1 over square root x minus 1 over 2 divided by x minus 4? So this time we have a complex fraction with radicals. That means we need to multiply the top and the bottom not only by the common denominator but also by the conjugate. But let's start with the common denominator. So I'm going to multiply the top and the bottom by these two. That is by 2 square root x. So when I multiply 1 over square root x times 2 square root x, the square root x terms will cancel, leaving behind positive 2. So I have the limit as x approaches 4 with a 2 on top. And if I multiply these two, the 2's will cancel, leaving behind the square root of x. And so on the bottom I have 2 square root x times x minus 4. So now my next step is to multiply the top and the bottom by the conjugate of the radical expression. That is by 2 plus square root x. Now I'm only going to FOIL the top part, not the bottom. So we have 2 times 2, which is 4. And then we have 2 times the square root of x. And then these two, that's going to be negative 2 square root x. And negative square root x times positive square root x is going to be negative square root x squared, which is negative x. And in the denominator, don't FOIL, just rewrite what you have. If you follow these steps, it won't be that difficult. So now 2 and negative 2 adds up to 0. So what we have left over is the limit as x approaches 4 of 4 minus x divided by all the stuff that we have on the bottom. Now what we're going to do at this point is we're going to factor out a negative 1. So this is now the limit as x approaches 4. So negative 1, and this is going to change to positive x, and plus 4 is going to change to negative 4, just like we did before. So now notice that we can cancel the x plus 4 terms at this point. So this is what we have left over. So now let's replace x with 4. So it's negative 1 divided by 2 square root 4 times 2 plus square root 4. So the square root of 4 is 2. And 2 times 2, that's going to be 4. And 2 plus 2 is 4. And 4 times 4 is 16. So the final answer is negative 1 divided by 16. And so that's going to be the limit. Now let's talk about how to evaluate limits graphically. So let's say if we want to calculate the limit as x approaches negative 3 from the left side. And let's say this graph represents the function f of x. So what can we do? So to evaluate the limit, you're looking for the y value. So first, identify where x is negative 3. X is negative 3 anywhere along that vertical line. Now we want to approach that vertical line from the left side. So therefore, you want to follow the curve from the left until you get to that point. So notice that the y value here corresponds to positive 1. So therefore, the limit as x approaches 3 from the left side is 1. Now what about from the right side? So you want to approach the vertical line at negative 3 from the right. So we got to follow this curve. So notice that the y value here is negative 3. So therefore, the limit as x approaches negative 3 from the right side, that's negative 3. Now what about the limit as x approaches negative 3 from either side? If the left-sided limit and the right-sided limit are not the same, then the limit does not exist. So these two are known as one-sided limits. Now what about f of negative 3? What is the value of the function when x is negative 3? To find it, identify the closed circle which has a y value of negative 3. So this is it. Now let's work on some more problems. So what is the limit as x approaches negative 2 from the left side? Go ahead and try this one. So identify the vertical line at negative 2. So we want to approach that line from the left side. So notice that the y value is negative 2. So what is the limit as x approaches negative 2 from the right side? So this time, we want to approach the vertical line from the right, and it points to the same value, negative 2. So therefore, the limit as x approaches negative 2 from either side does exist, because these two, they match. So therefore, it's going to be negative 2. Now, what is the function value when x is negative 2? So look for the closed circle that's on this vertical line. And so that's this point where the y value is positive 2. So as you can see, it's not very difficult to evaluate limits graphically. Now let me give you a new set of problems. Evaluate the limit as x approaches positive 1 from the left side, from the right side, and from either side, and also find the function value when x is 1. So x is 1 anywhere along that vertical line. So if we approach it from the left side, notice that the y value is positive 1 there. And if we approach it from the right side, the y value is 3. So because these two do not match, the limit as x approaches 1 does not exist. Now the function value at 1 is the closed circle, which has a y value of 2. Now here's the last set of problems like this. What is the limit as x approaches positive 3 from the left side and from the right side, and from either side, and then find the function value at 3. So notice that at x equals 3 we have this vertical asymptote. So as x approaches 3 from the from the left side, notice that it goes down to negative infinity. And as we approach 3 from the right side, it goes all the way up to positive infinity. Now these two do not match, so therefore the limit does not exist. And the function value at 3 is going to be undefined. So a good example of having a vertical asymptote at x equals 3 would be a function like this, 1 over x minus 3. And if you plug in 3, you're going to get 1 over 0, which is undefined. So whenever you have a 0 in the denominator, at that point you have a vertical asymptote, and it's undefined at that point. Now at negative 3, we have what is known as a jump discontinuity. The graph doesn't connect. at -2, we have what is known as a hole. A hole is a removable discontinuity. A jump discontinuity is not removable. So this is another example of a jump discontinuity. It's a non-removable discontinuity. And here we have an infinite discontinuity, which is also non-removable. Now, how can we evaluate this limit? What is the limit as x approaches 0 of 1 over x? Now, if we try to use direct substitution, 1 over 0 is undefined, so that's not going to work. Now, let's say if we plug in a number that's close to 0, like 0.1. 1 over 0.1 is 10. And if we plug in 0.01, 1 over 0.01 is 100. Notice that as x approaches 0 from the right side, it's getting larger and larger and larger. So we could say that the limit as x approaches 0 from the right of 1 over x will increase towards positive infinity. Now, if we plugged in -0.1, this would be -10. And if we plugged in -0.01, that's going to be -100. So therefore, we can come to the conclusion that the limit as x approaches 0 from the left side of 1 over x is -infinity. Now, because these two do not match, the limit does not exist. So for some limits, you need to check the left side and the right side, especially when you get 1 over 0. So here's another example. What is the limit as x approaches 3 of the function 1 over x minus 3 squared? Now, if we plug in 3, it's going to be 1 over 0. But as x approaches 3, we know that it's going to go either to positive or negative infinity. So let's check both sides. So here's a question for you. What is the limit as x approaches 3 from the right side? So if we plugged in 3.1, what will we get? So 1 over 3.1 minus 3 squared. So if you write it like this, this is equal to 100. Now f of 3.01, which is 1 over 3.01 minus 3 squared, that's going to give you 10,000. So therefore, as x approaches 3 from the right side, this is going to positive infinity. Now what about 3 from the left? So let's say if we plugged in 2.9. 2.9 minus 3 is -0.1, but once you square it, it's going to be positive. So therefore, we could say that this is going to approach positive infinity. So if you plug in numbers like 2.9 or 2.99, it's going to be same as the other numbers. You're going to get 100 and 1,000 as well. So therefore, this limit approaches positive infinity. Now, because infinity is not a number, some textbooks will still define this as the limit doesn't exist. But what it means is that the numbers keep getting larger, larger, and larger. It doesn't converge to a specific number. But you could write this as positive infinity if you want to. What is the limit as x approaches 0 of the function, the absolute value of x over x? Well, let's find out. So let's plug in 0.1. So the absolute value of 0.1 over 0.1, that's going to be 0.1 over 0.1, which is 1. And if we plug in -0.1, the absolute value of -0.1 is positive 0.1. And positive 0.1 divided by -0.1 is -1. So notice the difference between these two values. So what we can do is we could say that the limit as x approaches 0 from the right side, as represented by positive 0.1, that's going to equal positive 1. And the limit as x approaches 0 from the left side, as represented by negative 0.1, that's a negative 1. Now, because the right side and the left side limits do not match, as we know, this limit does not exist. So if you were to graph this function, what you're going to have is the jump discontinuity. So from 0 to the right, it looks like this is at 1, and 0 to the left is at negative 1. And so the limit doesn't exist due to this jump discontinuity. Now, sometimes you might be dealing with trigonometric functions. What is the limit as x approaches 0 of sine x over x? Now, this is something that you want to commit to memory. This is simply equal to 1. So make sure you know it. So based on that, what is the limit as x approaches 0 of sine 3x divided by 4x? And also, what is the limit as x approaches 0 of sine 7x over 5x? So for this one, it's simply 7 over 5. For the next example, it's 3 over 4. However, some teachers will want you to show your work, so let's do that. But if you want the quick answer, you can just literally see it. So how do we show our work? Using the fact that sine x over x as x approaches 0 is 1. So if that's true, we could say that the limit as u approaches 0 of sine u divided by u is 1 as well. So what we need to do is first make these two the same. In order to do that, I'm going to multiply the top and the bottom by 3 divided by 3. I'm going to move around some things. So I'm going to switch the 4 with the 3. 4 times 3 and 3 times 4 did the same thing. So I'm going to have sine 3x divided by 3x times 3 over 4. Now, I'm going to define u as 3x. So, as x approaches 0, 3x approaches 0, which means that u approaches 0, because 3 times 0 is still 0. So now, using substitution, I'm going to replace everything. So instead of x approaching 0, u is going to approach 0. And I'm going to replace 3x with the u variable. So I have sine u divided by u times 3 over 4. Now this expression here, that's equal to 1. So it's 1 times 3 over 4, which the final answer is 3 over 4. So that's how you can show your work with questions like these. So let me give you another example. What is the limit as x approaches 0 given the function tangent 5x divided by 3x? Now, the problem works the same way when you're dealing with sine and tangent, not with cosine. So this is going to be 5 over 3. But to show your work, we're going to use u substitution again. But first, let's rewrite this. So this is the limit as x approaches 0, tangent 5x over 1 times 1 over 3x. Now tangent is sine divided by cosine. So what we have now is sine 5x divided by cosine 5x times 1 over 3x. Now I need a 5x in the bottom. So I'm going to multiply the top and the bottom by 5. And I'm going to move around some things. So I'm going to keep the sign where it's located. And the x and the 5, I'm going to move it where cosine is. So now I have a 5 and a 3. So I'm just going to write 5 over 3. And I still have a cosine on the bottom. So now I'm going to set 5x equal to u. So this becomes the limit as u approaches 0, sine u divided by u times 1 over cosine u times 5 divided by 3. So, using the multiplication property of limits, what we could say is we now have the limit as u approaches 0 of sine u divided by u times the limit as u approaches 0 for 1 over cosine u, and then times 5 over 3. So this expression, we know it's equal to 1. Now, cosine of 0, we can use direct substitution for this one. Cosine of 0 is 1, and then we have times 5 over 3. So therefore, this is going to be the answer, 5 divided by 3. Consider the following piecewise function. So f of x is equal to 5x plus 3 whenever x is less than 1, and is equal to x squared plus 4 when x is equal to or greater than 1 but less than 3. And the function is equal to 3x minus 2 when x is equal to or greater than 3. So with this information, evaluate the following. What is the limit as x approaches 1? Now, in order to evaluate this limit, we need to find the limit as x approaches 1 from the left side and from the right side. So from the left side, which 3 portions of the piecewise function will you use? From the left of 1 is when x is less than 1, so we need to use 5x plus 3. So here we can use direct substitution. So it's 5 times 1 plus 3, which is going to be 8. So now let's do the same thing for the right side. So as x approaches 1 from the right, which of these 3 parts of the piecewise function should we use? 1 from the right is greater than 1, so we've got to use x squared plus 4. So that's going to be 1 squared plus 4, which is 5. So therefore, the left and the right side do not match. So this limit does not exist. Now, what if you're asked to find a function value at 4? What should you do? So x is 4 in this function because it's going to be greater than 3. So all you got to do is plug in 4 into 3x minus 2. And so that's 12 minus 2, that's 10. So whenever you have a piecewise function, you simply need to decide what portion of the piecewise function that you're dealing with. And you could find it based on this information, based on what x value you need to plug in. So for instance, what is the limit as x approaches 3 from the left side? So that's less than 3, which means we need to use that portion of the function. So we just got to replace x with 3, and this is going to be 9 plus 4, which is 13. So that's how you can evaluate limits using piecewise functions. Now, what is the limit as x approaches infinity of 1 over x? Now, whenever you have a large number in the denominator of a fraction, it's going to approach 0. Likewise, if you have a very small number in the bottom, it's going to approach infinity. So when the denominator is small, the value of the fraction is large. When the denominator is large, the value of the fraction is small. So this is going to approach 0. So for example, if x was 100, 1 over 100 is 0.01. If x was 1,000, 1 over 1,000 is 0.001. So whenever the denominator is bottom heavy, the value of the function will approach 0. Now let's say if we have the limit as x approaches infinity of, let's say, 8x plus 2 over 2x minus 5. Now, in this case, the function is not bottom heavy. The degree of the numerator is the same as that of the denominator. When you see that, you can just divide the coefficients. 8 divided by 2 is 4. Now, imagine if we plug in 1,000, a very large number. This would be 8 times 1,000 plus 2, and this would be 2 times 1,000 minus 5. So this would be 8,002 over 2,000 minus 5 is 1995. 8,002 is approximately 8,000. 1995 is approximately 2,000. So the answer is still close to 4. So when x becomes very large, the 2 and the negative 5 become insignificant. So you can eliminate it. So this becomes approximately 8x over 2x, which reduces to 4. So therefore, that's going to be the limit. It's going to approach 4. So if the degree of the top and the bottom is the same, just divide the coefficients if you want to get the quick answer. Now, if you want to show your work, here's what you can do. So multiply the top and the bottom by 1 over x. So we're going to have the limit as x approaches infinity, 8 plus 2 over x divided by 2 minus 5 over x. And keep in mind the limit as x approaches infinity of 1 over x is infinity. So I'm going to distribute the limit expression. So now I'm going to have 8 plus the limit, well, I'm going to take out the 2, plus 2 times the limit as x approaches infinity of 1 over x. And on the bottom, I'm going to have 2 minus 5 times the limit as x approaches infinity of 1 over x. So based on this expression, this is supposed to be 0, by the way, not infinity. This part is 0, and that is 0. So this is going to be 8 plus 2 times 0 over 2 minus 5 times 0, which in the end is 8 over 2, and that reduces to 4. So let's try another example like this. What is the limit as x approaches infinity of 9x squared minus 3x over 5x minus 3x squared plus 2? So go ahead and try that one. So looking at this, the degree of the top and the bottom is the same. So it's going to be 9 divided by negative 3, which is negative 3. So to show the work, let's multiply the top and the bottom by 1 over x squared. So this is going to be the limit as x approaches as x approaches infinity of 9 minus 3 over x divided by 5 over x minus 3 plus 2 over x squared. So this is going to be 9 minus 3 times the limit as x approaches infinity, 1 over x, and then this is going to be 5 times the limit as x approaches infinity, 1 over x, minus 3 plus 2 times the limit as x approaches infinity, 1 over x squared. And so this is going to be 9 minus 3. This is going to become 0. And that's going to be 0 as well. So that's 5 times 0 minus 3 plus 2 times 0. Because this one is still bottom heavy. So this becomes 9 divided by negative 3, which the final answer is negative 3.